Thank you for this kind introduction and need for the opportunity to address such a distinguished gathering. It is truly a pleasure to describe some of which were discussed over lunch. Again, if I may have that first slide. They include the cost and the time that it takes to develop new drugs. They include the problem of future pandemic preparedness, of course a pressing concern for us all in the light of the recent experience. And then finally, the third item on the list of the slide that you will see in a moment, I hope, the obvious purpose of not only curing or at least successfully treating disease, but preventing it in the first place. Again, if you can, so here's the first slide, which I have already spoken of, and I will tell you about ways in which these challenges, which are familiar to all of you and which are of long standing, can be addressed by new science, by new technologies flowing from that science. And I could present many examples that fall in these three categories. I happen to have chosen three examples that come from research and development in Israel, which I think is appropriate. But of course, if you like, I could offer also examples from many of the countries represented here that make major contributions to research and development along these lines. So in regard to the first, the cost and the time it takes to develop drugs, which has much to do with the ultimate cost of the drugs themselves spoken about at lunch today, the current approach to drug design, the current method by which new small molecule drugs are made is summarized here. It begins with determining the structure of a drug candidate bound to its target, followed by an attempt on the basis of that structure to make a change to the candidate expected to improve its efficacy, followed by chemical synthesis of the newly designed molecule and then testing. This is a process, a cycle, that is repeated over and over again in the hope of arriving finally at a successful drug molecule. As you may appreciate, this is an extremely costly and time-consuming process. Typically, hundreds of chemists will be engaged in the synthesis of thousands of molecules, and at the end, sometimes a drug is developed, but often the entire process ends in failure. The hope has been for a very long time that computation might contribute to improvement and also the best outcome of this approach. And what you will see here in the lower right is a symbol to indicate that calculations by computation of the interaction between a potential drug and its target rely upon classical physics. They can be accomplished rapidly in a matter of an hour or even minutes, but they result in an accuracy far, far less than what is indicated by the dashed line at the top, that needed to actually predict a successful drug. At the other extreme in the upper left, the true solution to the problem, which comes from fundamental chemistry called quantum mechanics, it will yield a precise result every time. The only problem is that such a calculation takes 1,000 billion years, and so obviously impractical. Finally, oh, excuse me. Shall I start over at the beginning? Finally, indicated here at the upper right, The newly developed approach, actually not so new, it took 20 years to do, but it's only finally succeeded in the last weeks and months, a version of the basic chemical, the quantum approach, which can be accomplished in a meaningful time and yields the desired accuracy. And I'm going to show you just one example to illustrate the power of that approach, and then comment which is the location of exact equivalence, so equality of the computation and the experimental measurement. And so you see the results with this new approach are highly successful in yielding computational results closely similar to those derived by experiment. In contrast, all of the computational methods available up until this time from both academic and commercial sources yield what are symbolized by the purple boxes and the pink triangles, results that are really not much better than random. Now, the significance of this, of course, is ultimately to replace chemistry, the cost and the time with computation, but also to be able to explore a far greater number of chemical possible solutions to the problem than could be done by the laborious method of synthesis. In this way, you can also make much better molecules, 1,000 times better at least, as has been shown, than those in use today, very rapidly, and thus by reducing the cost of development, and especially with better drugs, the cost of the clinical trials, the number of patients that are needed, the time that it takes, ultimately to produce results which will contribute to the goal that has been much discussed today of reducing the cost of medicine. Next, I'll turn to an example that relates to future pandemic preparedness. This example relates to an RNA molecule. It's a small RNA. It's called a small interfering RNA. Small interfering RNA, only about 20 RNA units in length, is a component of a natural pathway. So within every cell of every organism, there is a protein assembly which captures one strand of small interfering RNA, uses it to identify a messenger RNA for a protein, and upon recognition, destroy that message. This is a way of targeting and destroying unwanted proteins. For example, viral proteins in infected cells. Now, the problem, small interfering RNAs were discovered over 20 years ago, and their therapeutic promise was immediately appreciated. But there have been almost no new drugs made on this basis because these are large, electrically charged molecules. They do not penetrate cells. Delivery is the problem. You're well aware of the delivery problem because of the lengths to which one must go to deliver mRNA vaccines over the last couple of years. Vehicles which must be maintained at exceedingly low temperature, very difficult to produce, very expensive to do as well. Recently, here in Israel, a discovery was made of a simple modification illustrated on the right that could be made to a small interfering RNA, or indeed very many other molecules, such as a messenger RNA that one wishes to deliver to cells. This small modification, indeed, two such modifying moieties attached to an siRNA enable its rapid penetration in cells. On the left, a fluorescently labeled RNA, unmodified, fails to penetrate. On the right, a fluorescently labeled molecule, modified in this manner, penetrates every cell rapidly. And finally, here is an example of an application for the creation of a SARS-CoV-2 drug, tested in non-human primates, which are the preferred system for comparison with the human respiratory system. And what you see is that following infection of the monkeys with SARS-CoV-2, delivery of this SARS-CoV-2 small interfering RNA resulted in a 99.9% reduction in viral load over a period of days. It's important to note that small interfering RNAs are not only therapeutic, but because it is a natural mechanism, they persist in our cells for weeks. And so a single inhalation of a drug of this kind will protect against infection for a significant length of time. Now, mRNA, small interfering RNA, proteins, peptides modified in this manner for delivery to human cells can be formulated as aqueous solutions or even dry powders, so they can be distributed around the world at very low cost, maintained indefinitely at a room or even slightly elevated temperature. It's not less important that the synthesis of a small interfering RNA, it can be done on a machine. It can be programmed and done automatically. And this enables the immediate production of a suitable small interfering RNA with the appropriate sequence of the RNA to all human respiratory viruses. So you may not know that until recently there was only one drug for any one of the 23 common human respiratory viruses. This method can be used this year to produce effective drugs, indeed prophylactic measures, for all 23 human respiratory viruses, and it could, if distributed around the world, result in the elimination of human respiratory disease in the same manner as has been achieved with vaccination for polio, for example. Finally, in the last couple of minutes, I'd like to comment on the third aspect that I mentioned at the outset of no less concern to all of us, and that is not just cure or therapy, but prevention of disease in the first place. And I'll take an example that is very well known to you, that of air pollution, especially of small particulates, so-called PM2.5s, 2.5 micron particles. These are the most common pollutant, and as you're all doubtless aware, they increase the risk of respiratory and cardiovascular disease and even damage the immune system. What not everyone realizes is that indoor air pollution is actually a far greater concern, a human health concern, than outdoor air pollution, at least 5 times greater concern, where people spend indoors 90% of their time, and where indoor air pollution can result from cooking, from aerosols, and other sources. The new technology that was developed in Israel to address this problem is of great significance because of an estimate that was made a couple of years ago of the hazard posed by air pollution. Not only 6.5 million people believed to have died in 2019, but greater than 93 billion days of illness, with an extraordinary economic cost over $5 trillion to the world. So the approach that was developed here is software that can be installed in any cell phone that relies only upon the existing, rather primitive, audio and camera capabilities of the phone, which transforms it into an accurate weather station, one that can measure and report both to the user and, if you will, to doctors or health authorities, the temperature, the concentration of PM2.5s in the air, UV light, sound, other hazards to the user. The measurements are extraordinarily accurate. For example, in the case of temperature, within 1 degree centigrade, you may ask, how could a cell phone armed only with audio and visual capabilities measure temperature so accurately? Well, that is part of the genius of those who developed this approach. The significance is very great because, first of all, it will provide a personal warning system to the user that they are endangered by some aspect of the environment around them. Of course, it can conserve energy in a dramatic way because it will not be necessary to heat, cool, filter air, or what have you for every building in which one resides, but only in the immediate vicinity of the user. And perhaps most important of all, and of concern to those of you here, it will ultimately, if deployed on millions, perhaps hundreds of millions, even billions of phones, provide an extraordinary trove of data useful to health authorities, to insurance companies, to governments for city planning and what have you. With that, I'd like to conclude with a remark that I had not planned, but which seemed to me important in light of what I heard discussed over the course of lunch today. It is, if you will, a plea for the science of the future, and let me explain in the following way. We know less than 1% of what there is to know about human biology, and all of the medicine that was discussed over lunch and that I have spoken of here flows from knowledge of less than 1% of human biology. Imagine what would be possible if we knew the other 99%. Not just medicines that are palliative, not just medicines that can extend life, but ultimately medicines that will cure all disease. Indeed, I didn't have time now, but I could tell you that even with what I've told you today, I believe I could convince you about the prospects of not just alleviating but curing many cancers, the prospect of stopping Alzheimer's disease in its tracks wherever it arises, and so forth. Much, much more will be possible with the discovery of the science which underlies. I did not have time to explain that everything that I spoke is threatened today. You may not be aware, but the goose that laid those golden eggs is dreadfully imperiled. Young people today are not pursuing careers in science in the same way as in my own life and that of many of you. When I started as a student, an undergraduate student, on my career at Harvard College 60 years ago, I was surrounded by young people whose dream, whose mission, whose desire in life was to discover fundamental facts of nature, which ultimately led to everything that I've told you and almost every medicine that you know about. For the most part, young people today are not pursuing such careers with the same enthusiasm. And we, all of us here, and everyone else in a position to do so, must find ways to encourage the pursuit of basic knowledge for these laudable purposes. Thank you very much.